Welcome to this video. Today, we'll be tackling problem number 413, arithmetic slices. This problem is a great exercise in understanding arithmetic sequences and how to efficiently identify patterns within an array. Stay tuned as we break this down step by step and explore a variety of approaches to solve it. In this problem, we are working with sequences of numbers and identifying a special type of subarray called an arithmetic slice. First, let's understand what an arithmetic sequence is. A sequence is considered arithmetic if the difference between any two consecutive elements remains constant. For example, in the sequence 1, 3, 5, 7, 9, the difference between consecutive elements is always 2, so it's arithmetic. Similarly, the sequence 7, 7, 7, 7 is also arithmetic because the difference is consistently 0. Now, the task is to find all subarrays of at least length 3 that form an arithmetic sequence in the given array nums. These subarrays are what we call arithmetic slices. The input is an array of integers, nums, and the output is a single integer that represents the total number of such arithmetic slices. Since the array can be large, with up to 5,000 elements, and the values can range between -1 million and 1 million, efficiency is important. Let's consider the first example where nums is 1, 2, 3, 4. The output is 3, which means there are 3 arithmetic slices. These slices are 1, 2, 3, 2, 3, 4, and 1, 2, 3, 4. The first slice, 1, 2, 3, is arithmetic because the difference between consecutive elements is 1. Similarly, 2, 3, 4 has the same consistent difference, and the entire array 1, 2, 3, 4 also maintains this difference throughout. Notice that each of these slices has at least 3 elements, which satisfies the minimum length requirement. So for this input, the total count of arithmetic slices is 3. Now take the second example where nums is 1. The output here is 0 because there are no subarrays of length 3 or more. Remember, the definition of an arithmetic slice requires a subarray to have at least 3 elements, and since this array only has 1 element, it's impossible to form any valid slices. This example highlights a key point: if the input array has fewer than 3 elements, the result will always be 0, as no subarray can meet the minimum length requirement. In the third example, the input is 1, 3, 5, 7, 9, and the output is 6. Let's break this down. The arithmetic slices here are 1, 3, 5, 3, 5, 7, 5, 7, 9, 1, 3, 5, 7, 3, 5, 7, 9, and 1, 3, 5, 7, 9. The first 3 slices each have 3 elements, and the difference between consecutive elements is consistently 2 across all cases. The next 2 slices are longer, with 4 elements each, and they also maintain the same difference. Finally, the entire array is a valid slice because it maintains this consistent difference throughout. In total, there are 6 valid slices, so the result is 6. To wrap up, there are some important edge cases to consider. If the array nums has fewer than 3 elements, the result is always 0 because no subarray can meet the minimum length requirement. If all the elements in nums are the same, every subarray of length 3 or more is an arithmetic slice since the difference between consecutive elements will always be 0. For arrays that are strictly increasing or decreasing, the result depends on how consistently the difference is maintained across the elements. Finally, because the input size can be as large as 5,000 elements, it's crucial to handle large arrays efficiently to ensure the solution performs well within the given constraints. To solve the problem of counting arithmetic slices in an array, we first consider the brute force approach. The intuition here is straightforward: we check all possible subarrays of size 3 or more and verify if each one forms an arithmetic sequence. This involves using 2 nested loops to generate all potential subarrays and a third loop to check if the difference between consecutive elements remains constant across the subarray. If it does, we increment our count for valid slices. While this approach is conceptually simple, the downside is its inefficiency. With a cubic time complexity of n cubed, it becomes impractical for large arrays, as the computational cost grows rapidly with input size. This inefficiency motivates us to explore more optimized solutions. To address the inefficiency of the brute force method, we turn to a dynamic programming approach. The key insight here is that if a subarray ending at index I1 is arithmetic, then appending one more element at index I will also result in an arithmetic subarray, provided the common difference remains constant. This allows us to define overlapping subproblems, leading to an efficient DP solution. We define a DP I array where each value represents the number of arithmetic slices ending at index I. If the difference between consecutive elements remains the same, we update DP I to be DP I1 plus 1. Otherwise, we reset it to 0. Summing up all values in the DP array gives us the total count of arithmetic slices. While this approach reduces the time complexity to O(n), it still requires extra space for the DP array. To optimize further, we notice that the value of DP I only depends on the previous state, allowing us to implement a space-efficient variation. By maintaining a single variable for the current state and another for the total count, we achieve the same result with a time complexity of O(n) and a space complexity of O(1). This makes the optimized space approach both efficient and practical for implementation. The strategy we ultimately select is the optimized space approach, as it offers the best balance between efficiency and simplicity. The intuition behind this approach lies in recognizing that arithmetic subarrays naturally extend from previous ones when the common difference remains unchanged. By iterating through the array just once and maintaining two variables, one to track the current count of arithmetic slices and another to accumulate the total count, we eliminate the need for additional space while leveraging the recurrence relation dp I equals dp I1 plus 1. This realization streamlines the computation process. The aha moment came from understanding that we don't need to store the entire DP array, as the state of any index depends solely on the previous one. This significantly reduces overhead and allows us to solve the problem in an elegant and scalable manner. When comparing the three approaches, the trade-offs become clear. The brute force method, while intuitive, is computationally prohibitive due to its cubic complexity and is unsuitable for larger input sizes. The dynamic programming approach improves efficiency by reducing the time complexity to O(n), but it still requires additional space for the DP array. The optimized space approach, however, achieves the same optimal time complexity while using only constant space. This makes it the best overall choice for this problem. We chose this approach not only for its efficiency but also for its simplicity and scalability. It is easy to implement, understand, and performs exceptionally well even for large arrays, making it the ideal solution for the problem at hand. In this problem, we need to count subarrays of size 3 or greater that form an arithmetic sequence. An arithmetic sequence is a series of numbers where the difference between consecutive elements remains constant. To solve this, we can start by using a brute force approach. Here's the idea: we iterate through all possible subarrays of size 3 or more and check each one to see if it meets the criteria of an arithmetic sequence. To do this, we use two nested loops. The outer loop starts at the beginning of the array and goes to the second to last element, and the inner loop progressively extends the size of the subarray from the current index of the outer loop. For each subarray, we ensure that its size is at least 3 before performing further checks. This method guarantees that we examine all potential subarrays but can be computationally expensive. Once we identify a subarray of size 3 or more, we check if it forms an arithmetic sequence. This involves computing the common difference, denoted as D, which is the difference between the first two elements of the subarray. We then traverse the subarray and confirm that the difference between all consecutive elements matches D. If this condition is satisfied for the entire subarray, it is considered valid. To keep track of valid subarrays, we maintain a counter that increments each time we find one. At the end of this process, the counter will hold the total number of valid arithmetic subarrays. While this brute force approach is straightforward, it involves significant redundancy and inefficiencies, which we'll address with an optimized approach. The optimized approach focuses on dynamically extending and counting valid subarrays as we traverse the array. To optimize the solution, we take advantage of the properties of arithmetic sequences and eliminate redundant checks. First, we initialize two variables, count, which stores the total number of valid subarrays, and current_length, which tracks the length of the current arithmetic subarray. Then, we traverse the array, starting from the second element. For each pair of consecutive elements, we calculate their difference. If the current difference matches the previous difference, it means the arithmetic sequence continues. We increment current_length to reflect the extended sequence and add current_length 2 to count, since all subarrays ending at the current position are valid. If the difference does not match, we reset current_length to 2, indicating the start of a new sequence. This dynamic approach ensures that we count valid subarrays efficiently during a single traversal of the array. Several key insights can help us better understand this problem. First, subarrays of size less than 3 cannot form an arithmetic sequence, so we can exclude them immediately. Second, the brute force approach involves many redundant checks, as it explicitly examines all possible subarrays, a process that becomes computationally expensive for large arrays. The optimized approach avoids this by dynamically extending valid subarrays and counting them on the fly. Additionally, we must consider edge cases. For example, if the array has fewer than 3 elements, the output must be 0, as no arithmetic subarrays can exist. Similarly, if the array contains no valid arithmetic subarrays, the output should also be 0. Finally, in cases where all elements of the array are the same, every subarray of size 3 or more is valid, as the difference between consecutive elements is consistently 0. To solve this problem, we rely on a few simple data structures. The input data is stored in an array, which we traverse to identify arithmetic subarrays. In addition, we use two variables, count, which keeps track of the total number of valid subarrays, and current_length, which monitors the size of the current arithmetic subarray. These variables allow us to dynamically count valid subarrays without requiring extra space for storing intermediate results. The simplicity of these data structures contributes to the efficiency of the optimized approach, making it well-suited for handling larger inputs. Now, let's analyze the time complexity of the two approaches. For the brute force method, generating all subarrays of size 3 or more requires n^2 operations, and verifying whether each subarray is arithmetic takes an additional n time. This results in a total time complexity of n^3, which is impractical for large arrays. On the other hand, the optimized approach only requires a single traversal of the array, making it n. This dramatic improvement is achieved by dynamically extending and counting valid subarrays instead of rechecking overlapping elements. Thus, the optimized approach is far more efficient and scalable. Let's walk through an example to see how the optimized approach works. Given the array 1, 3, 5, 7, 9, we start by initializing count to 0 and current_length to 2. Comparing differences between consecutive elements, we find that 3 minus 1 equals 2, marking the start of a new arithmetic sequence. We increment current_length to 3 and add 1 to count. Next, 5 to 3 is also 2, so we extend the sequence, set current_length to 4, and add 2 to count. Similarly, 7 to 5 and 9 to 7 both equal 2, so we continue extending the sequence, updating current_length and adding 3 and 4 to count, respectively. At the end, count equals 10, which is the total number of valid arithmetic subarrays. This example demonstrates the efficiency of the optimized approach in dynamically identifying and counting valid subarrays. This solution aims to efficiently count the number of arithmetic slices in the input array nums. An arithmetic slice is a subarray of at least 3 elements where the difference between consecutive elements is constant. First, we handle the edge case. If the array has fewer than 3 elements, it's impossible to have an arithmetic slice, so we return 0 immediately. We initialize two variables, count, which stores the total number of arithmetic slices, and current, which tracks the number of consecutive arithmetic slices ending at the current index. The main loop starts at index 2 since we need at least 3 elements to form an arithmetic slice. At each step, we check if the current difference between nums I and nums I1 matches the previous difference between nums I1 and nums I2. If they match, it means the sequence is continuing an arithmetic pattern. In this case, we increment current, indicating an additional arithmetic slice ending at index I, and add current to count. If the differences don't match, the arithmetic pattern is broken, so we reset current to 0. Finally, after the loop, the variable count contains the total number of arithmetic slices in the array, which we return as the result. This approach efficiently solves the problem in n time, where n is the length of the input array. This is the Java implementation of the arithmetic slices problem, LeetCode number 413. The solution mirrors the logic of the provided Python implementation, with a loop that checks for arithmetic progressions in the input array. Key differences include the use of explicit type declarations for variables in Java's array syntax. The method efficiently calculates the number of arithmetic slices by maintaining a running count of valid subarrays and adds them to the total count whenever a valid slice is found. To solve this problem, we need to identify arithmetic slices in the input array, which are subarrays of at least 3 elements where the difference between consecutive elements remains the same. Let's start with example 1, where the input is 1, 2, 3, 4. First, we initialize 2 variables. Count is set to 0 to store the total number of arithmetic slices, and current is also set to 0 to keep track of the number of consecutive slices ending at the current index. Since an arithmetic slice requires at least 3 elements, we begin iterating from index 2. At this index, we calculate the differences between consecutive elements nums 2, nums 1 equals 1, and nums 1, nums 0 also equals 1. The differences are equal, so we detect an arithmetic slice ending at index 2. We increment current by 1, making it 1, and add this value to count, resulting in a total count of 1 so far. At index 3, we perform the same calculation. The difference nums 3, nums 2 equals 1, and nums 2, nums 1 also equals 1. Since the differences remain equal, this extends the slice. We increment current by 1 again, so current now becomes 2. Adding this to count brings the total to 3. This means that by the end of the loop, we have identified 3 arithmetic slices 1, 2, 3, 2, 3, 4, and 1, 2, 3, 4. Thus, the output for this example is 3. Now, in example 2, the input is 1, 3, 5, 7, 9. We start by initializing count and current to 0 as before, and begin iterating to check for arithmetic slices. At index 2, we calculate the differences nums 2, nums 1 equals 2, and nums 1, nums 0 also equals 2. Since the differences are equal, we have an arithmetic slice ending at index 2. We increment current to 1 and add it to count, bringing count to 1. At index 3, the difference is nums 3, nums 2, and nums 2, nums 1, both equal 2, so the slice extends. We increment current to 2 and add it to count, making the total 3. At index 4, the difference is nums 4, nums 3, and nums 3, nums 2 remain 2. Again, the slice extends, so current becomes 3. And adding this to count results in a final total of 6. The slices identified include 1, 3, 5, 3, 5, 7, 5, 7, 9, 1, 3, 5, 7, 3, 5, 7, 9, and 1, 3, 5, 7, 9. The output is 6. In example 3, the input is 1, 1, 2, 5, 7. Again, we initialize count and current to 0. At index 2, we calculate the differences nums 2, nums 1 equals 1, but nums 1, nums 0 equals 0. Since the differences are not equal, this breaks the arithmetic sequence, and we reset current to 0. Similarly, at index 3, the differences nums 3, nums 2, and nums 2, nums 1 are 3 and 1, respectively, which are also not equal, so current remains 0. At index 4, the differences nums 4, nums 3, and nums 3, nums 2 are 2 and 3, which again are not equal. Since no arithmetic slices are detected throughout the array, count remains 0. Thus, the output for this example is 0. The time complexity of our solution is O, n, where n represents the length of the input array nums. This efficiency stems from the algorithm structure, which involves a single iteration over the array. Starting from the third element, the loop runs from index 2 to the end of the array, ensuring exactly in 2 iterations in the worst-case scenario. Within each iteration, the operations such as checking for arithmetic progression, updating the current count of slices, and adding to the total count are all performed in constant time, or O1. Thus, the overall contribution to the time complexity is strictly linear, or O(n). In terms of best, average, and worst cases, the algorithm performs differently based on the input size. If the array has fewer than 3 elements, the algorithm immediately returns 0, which is O(1). For typical cases, where the entire array is processed, the complexity remains O(n). Even in the worst-case scenario, the algorithm continues to maintain an O(n) complexity since the entire array is traversed linearly. The space complexity of this solution is O(1), meaning it uses a constant amount of additional memory, regardless of the input size. This is achieved by utilizing only two integer variables, count to record the total number of arithmetic slices in the array, and current to track the running count of valid slices during the iteration. There are no additional data structures such as arrays or lists being created, nor is there any recursive stack involved. Furthermore, the algorithm accesses the input array nums directly without making a copy, ensuring no extra space is allocated. As a result, the overall space usage remains constant, making the space complexity O(1). When comparing our optimized solution to a brute force approach, the advantages become clear. A naive method would involve generating all possible subarrays of size 3 or more and then checking if each subarray forms an arithmetic sequence. This process has significant computational overhead. Specifically, generating all subarrays requires iterating over all possible start and end indices, which results in O(n²) subarrays. For each subarray, verifying if it is arithmetic involves iterating through its elements, adding an additional O(k) factor, where k is the length of the subarray. Combining these steps, the overall time complexity of the brute force approach becomes O(n³ in the worst case. Additionally, the space complexity of the brute force method is O(n²), because it requires storing all the generated subarrays. This comparison highlights the inefficiency of the brute force method, especially for larger arrays. The current solution significantly optimizes both time and space complexity compared to the brute force approach. Instead of generating and verifying subarrays, it maintains a running count of valid slices directly, reducing the time complexity to O(n). This is achieved by performing a single traversal of the input array, where each operation inside the loop, such as checking conditions, updating counters, and summing values, is executed in constant time, or O(1). Mathematically, this gives us a total time complexity of O(n)(2) times O(1), which simplifies to O(n). Additionally, the space complexity remains constant at O(1), because the algorithm uses only two integer variables, count and current, and does not rely on any additional data structures. These optimizations make the solution both efficient and scalable for large input sizes. When solving the arithmetic slices problem, there are several common pitfalls to watch out for. First, not handling edge cases properly is a frequent mistake. For example, arrays with fewer than 3 elements, arrays where all elements are identical, or arrays with no valid arithmetic subarrays can lead to incorrect results if not accounted for. It's essential to test these scenarios explicitly. Another mistake is relying on an inefficient brute force approach that generates all possible subarrays. This can result in time complexity as high as O(n³) and become infeasible for larger inputs. Additionally, solutions that check only the first and second differences to verify arithmetic sequences often fail for longer subarrays, as they don't ensure the same difference is maintained throughout. Lastly, overcomplicating optimized approaches like the sliding window method by adding unnecessary checks can lead to logical errors and make the code harder to read. Staying mindful of these issues can significantly improve both the efficiency and accuracy of your solution. Now, let's consider another common mistake: ignoring integer overflow issues in languages like Java or C++. When working with large integers, operations such as computing differences can lead to overflow errors. To avoid this, always use appropriate data types that can handle large values. Beyond avoiding mistakes, there are several strategies to excel in interviews. Optimization is critical. While brute force methods are a good starting point, interviewers typically expect you to find patterns, such as the constant differences in arithmetic sequences, and optimize your solution accordingly. Techniques like sliding windows or dynamic programming are often preferred for their efficiency and may be part of follow-up questions. Clear communication is also key. As you transition from a brute force approach to an optimized solution, make sure to articulate your thought process clearly. Finally, testing edge cases is a must before you finalize your solution. Explicitly consider scenarios like empty arrays, arrays with fewer than 3 elements, or arrays with repeated numbers to ensure robustness. To deepen your understanding of this problem, it's helpful to explore related LeetCode problems. For instance, problem 413, arithmetic slices, is a foundational problem that focuses on counting arithmetic subarrays using optimized methods. Another related problem is LeetCode 560, subarray sum equals k, which involves finding subarrays with a specific sum using techniques like sliding windows and prefix sums. LeetCode 238, product of array except self, while not directly related to arithmetic slices, emphasizes efficient array manipulation, a skill that's valuable in many array-based problems. Lastly, LeetCode 209, minimum size subarray sum, is another subarray problem that uses sliding window techniques for optimization. Studying these problems will help you refine your approach to subarray problems and improve your overall problem-solving skills. Finally, let's compare some alternative approaches to solving this problem and their trade-offs. The brute force approach is the simplest to implement but has a time complexity of n cubed, making it inefficient for larger inputs. It's mainly useful as a baseline solution or for small input sizes. The sliding window approach is more efficient, typically achieving n squared time complexity, but it requires careful implementation to ensure correctness. This approach is ideal for larger inputs and is often the expected solution in interviews once you've established the basics. Dynamic programming is another powerful option. It reduces redundant computations by reusing intermediate results, which makes it highly efficient. However, it can be more complex to design and implement. Dynamic programming is particularly well suited for problems with overlapping subproblems. Understanding the trade-offs between these approaches will help you choose the most appropriate method based on the problem's constraints and requirements. Great job! We've reviewed the key aspects of solving problem number 413, arithmetic slices. Remember the importance of identifying patterns and optimizing for performance. Don't forget to subscribe for more coding challenges, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!